All right, hey everybody, it's Miss Manili, and I'm going to give you your last AP Stat lesson of the year on inference for linear regression. Everybody in my 2B class, say hey! All right. Okay, we're going to start with a quick warm-up that reviews our linear regression procedures that we learned way back in the beginning of the year. All right, so you want to make sure that you enter all of your TV hours in list 1, your GPA data in list 2. Yep. The whole time. All right, so once your data is entered, and first of all, let's talk about what this problem represents. It says we have a random sample of 10 high school students who produce the following results for the number of the number of hours of television watched per week and their GPA. So we're ultimately trying to determine if there's a relationship between how much TV you watch and your GPA. We might expect that if you're spending more time watching TV than doing your schoolwork, that your GPA might suffer, and so we might expect a negative association. So you're given a scatter plot, but if you forget how to construct the scatter plot, once your data is entered in list 1 and list 2, if you go to second y equals, you can set up your scatter plot. I want to make sure you turn it on. The very first graph is your scatter plot, and then you want to make sure that you're pulling your x and y lists from the appropriate list. So I've got them in list 1 and list 2. Now, right now my calculator is in alpha mode, so if I want to do a zoom 9 and actually see the scatter plot, and that's what I've got. I also have an equation graphed. All right, so in my case, I've got a bunch of equations that I need to delete. Otherwise, they're going to conflict with my scatter plot. All right, so there we go. So when you're asked to describe the association, remember when it's two variables, okay, our scatter plot, we have to talk about the form, the strength, and the direction. The strength and direction are probably pretty obvious, but what do we mean by form? Is it linear? Okay, so when looking at the scatter plot, let's first of all label the axes. What does the x-axis represent? TV hours. And what about the y-axis? GPA. Okay, so how would you describe the strength, the form, and the direction using the context of the problem? Because on the AP exam, everything you write needs to be in the context of the problem. So who can tell me what they would write here? Can I get a volunteer? You don't have to speak into the microphone. Go ahead, Casey. You want to? Yeah. Just talk really loud. Okay. Yeah, put it in the context of the problem. There's a negative association between TV hours and GPA. Okay. Do you have more to that? Okay. A moderate. Want to throw linear in there somewhere? So maybe a moderately, that should be a y, sorry, moderately linear. It is pretty subjective. But there is a value that we can look at that will help us make it a little bit more objective. What is it? What did you say? R squared and what else? R. R in and of itself, our correlation coefficient, describes the strength and direction and gives us a more objective figure. When you're just looking at the scatter plot, it is relatively subjective. Okay, so there's a negative association between TV hours and GPA. You could also say that in general, the more TV watched, the lower the GPA. All right. So the next thing we're asked to do, guys, with me? The next thing we're asked to do is to determine the least squares regression line. Anytime it's referring to least squares regression, it's always talking about linear regression. Okay, so least squares means linear. So if we go to our stat calc menu, now the one thing I do want to just point out is your calculator has two linear regression commands. There's the command that's used option 4, and notice that in this command it's ax plus b, where the variable a represents your slope and b represents your y-intercept. If you scroll down a little bit further, there's another command for linear regression, but it's in a different form, where a is actually your y-intercept and b is your slope. I don't want you to get too hung up in the A and the B, but I do want you to recognize that in all of our inference techniques, we're referring to A as our y-intercept and B as our slope. So if you're using the first command, I don't want you to get the a's and the b's confused. So just remember, your slope is always going to be your coefficient of x. And if you just kind of keep that in mind, then it shouldn't matter if it's called a or b or m. It doesn't matter. Okay, so either of those commands will give you the correct equation. Just make sure you tell the calculator where the data is. We're not using a frequency list, so we can leave that blank. We do want to make sure that the calculator stores the regression equation in y equals. So to get there, we go to vars, y vars, and then click function, and then you can store your regression equation in any of those. I'm going to go ahead and do it in y1, and then calculate. Okay, and so remember, when you're writing your regression equation, it's just from sample data. It's an estimate, so we put a little hat on the y, and that would be equal to, in this case, a is our y-intercept, so it's going to be 3.823 plus our slope. Actually, it's a minus, isn't it? Minus 0.065 times x. Is that what everybody got? Okay. Now, if you don't have r and r squared on your calculator, you have to go to your catalog. So you're going to go to second catalog and then scroll down until it says diagnostics on, and then turn them on. Okay. So you're asked to interpret the slope and the y-intercept in the context of the problem. So let's talk about the slope. What does this negative 0.065 mean in the context of the problem? Okay, for every hour of TV watched in a week, GPA. Now, we want to be careful when we're describing the slope and the y-intercept from a regression equation, because this isn't necessarily going to be what happens for everybody. It's not necessarily what's always happening. So we want to make sure that we're describing like an estimate or an approximation. So we could say the GPA is estimated to decrease 0.065 points. Okay, so you do want to make sure that you're using the estimated or approximately or on average, that you're not describing it as being an exact value that's going to happen for everybody. And then what about the y-intercept? Our y-intercept is 3.823. What does that represent? Yeah, so this would be the estimated GPA of a student watching 0 hours of TV. Okay, and again, this is just an estimated or an overall average. And sometimes you'll find that your y-intercept doesn't make any sense in a problem. So for example, let's say this was like 15 something. Can anybody explain why sometimes the y-intercept doesn't make any sense for a problem? Exactly. So when our y-intercept is really located far away from all of our data points, sometimes, because we're looking at a line that extends forever, sometimes where it crosses the y-axis really is unreasonable considering where the rest of our data is. And there's a term that we use for that. Anytime you're making a prediction that goes beyond the data, extrapolation. An outlier is a point on the graph that is outside the rest of the pattern. But when we're making a prediction that's beyond our data, that's what we call extrapolation. Okay. The next thing you're asked to do is to state the values of r and r squared and then describe what they mean. So in this case, r is negative 0.814. And so r, what does that tell us? The correlation coefficient describes what? The strength and direction, which is pretty much what we were describing in that very first sentence. This tells us that there's going to be a moderately strong or moderate negative association. You want to be careful about saying that it represents a linear relationship without looking at the scatter plot. Because if all you're doing is looking at a value of r and you don't actually see the plot itself, you really can't say whether or not it's linear. So r alone just describes the strength and direction. Does anybody remember how to interpret r squared? Let me give somebody else a shot. Grace? Okay, close. So r squared in this case is 0.662, which basically is telling us that 66.2%, now it's not of the data, we're saying of the variation in the y variable. Because remember, when we looked, if I go back to my graph for a second, and now I see my regression line cutting through the points, it doesn't hit every point. So r squared describes the scatter of y values that are around the graph. So 60% of that scatter, 66% of the variation in the y variable, which in this case is GPA, is explained by or accounted for the regression equation. And we want to make sure we refer back to our explanatory variable on TV hours. Okay? The next thing you're asked to do is to construct a residual plot. You've got the steps to do that on your paper. I didn't feel like squeezing them in here. But for all of the inference techniques that you're going to be doing, every single problem is going to require a scatter plot of the original data of x versus y, a residual plot of x versus your residuals, and it's also going to require, this is a new one, a normal probability plot of the residuals. So every single problem regarding inference on regression is going to require those three graphs. So let's review how to come up with the residual plot. It does take a few steps. So just to remember what a residual is, the residual is that difference or the distance between our point and our line. So the residual is basically, I can't draw on my smartboard over here, but it's basically the distance between every point and the line, that vertical distance. Okay? So a residual plot is essentially just going to turn this graph sideways so that my regression equation is a horizontal line, and we can focus on the scatter of points about that line. It makes a little bit more sense if you're dealing with a curve, because the residual plot will straighten out the curve, and then you can really examine the scatter. I didn't mean to do that. Okay, so we're going to go back into our lists if you haven't done this already. What we need to do is put our predicted values in list 3. So a residual is always going to be your observed y value minus the predicted. And so to get the predicted, I have to insert my equation. So I'm going to go to vars, y vars. I'm going to pick the function where I've stored my regression equation, and then I'm just using function notation. So instead of saying f of x, I'm going to use y1, and all of my x's are listed in list 1. And so this command is basically going to evaluate the equation for every single value of x that's listed in list 1. And I can see if I compare the values in list 2 and list 3, the values are pretty close. To come up with the residual, though, I actually want to subtract my actual minus the observed, which is going to be list 2 minus list 3. I said actual minus observed. Observed minus predicted is what I meant to say. So a residual is observed, which is also the actual data, minus what we would predict from our equation. And so you'll notice that some of those values are positive and some of them are negative because you have points above and points below the line. What do you think would happen if I added them all up? They should equal 0. They should cancel each other out. Okay, so to do a residual plot, we're going to go back into our scatter plot menu. We're still going to keep the original scatter plot, but we're going to change the y list to list 4, because now I'm just going to examine all my x's and all those distances. And if I hit zoom 9, I'll see a different pattern, or I'll see a different scatter plot, where this horizontal line is now my regression equation. And so we're just sketching. So it looks like I have a point here, and we're just going to sketch what we see. Doesn't have to be perfect. But in terms of interpreting a residual plot, what are the things that we look for, or what are the things that we don't want to see? We don't want to see any patterns, because a pattern would indicate that a linear model is not appropriate. So what looks good in a scatter plot? I mean, in a residual plot? random. We want to have a random scatter of points. We want to make sure there's an even distribution above the regression equation as well as below. If there's any clusters, if there's any points that are significantly further away from the rest of the points, then that's not a good sign. So tell me about this graph. Is it okay? Is it a good representation? So something like this, where we know that there's an even scatter of points around the line, tells us that the linear model is appropriate. So the even scatter of points, that shouldn't be a comma, tells us a linear model is appropriate. Okay. And so knowing that the linear model is appropriate, now lets me go ahead and I can make predictions. So in letter E, it says to use your regression equation to estimate the GPA of a student who watches 15 hours of television per week. So the way I can do that, there's several ways that we can calculate it. Essentially, I'm plugging in the 15 for x. Since I already have my function in y1, I can, again, use function notation in my home screen and just evaluate y1 at 15. And that'll give me a GPA of 2.85. Are we confident in that? Why? How come we're confident in that? Yeah, the 15 hours of television per week is within our data range. And if you compare that GPA to what we have in our table, it seems to fit pretty reasonably. But what about in letter F? If I do the same command but change 15 hours to 30, I get a prediction, but how reliable is it? Why is it not reliable? Yes, it's an extrapolation. Exactly. 30 is too far beyond our data to be confident. We don't have any data to support our model after, what is it, 24 hours, I think was the biggest number? Okay. All right, any questions about the warm-up? Okay. Okay. So we're going to start talking about inference for regression. We're only going to be looking at inference for the slope of a linear regression equation. There are other types of inference for regression procedures, but we're only going to be looking at slope. And we're looking at the rate of change between two quantitative variables. So we're going to be looking at confidence intervals for slope as well as tests of significance for slope to see if there's an association between quantitative variables. So those are our objectives for today. There are a lot more symbols that we're going to be using since our equations are different. We're not talking about a mean or a standard deviation or a proportion. We're dealing with slope and y-intercept. All right, so introduction. When a scatter plot shows a linear relationship, and this time we're talking about quantitative data again. Remember with chi-squared, we were looking at relationships between quantitative variables, categorical variables. Now we're moving back to quantitative. So we can use the least squares regression line fitted to the data to predict a y for any given value of x. If our data come from a random sample, then we also can make inferences about the population. And so some of the questions that we try to answer would be like, is there really a linear relationship between x and y in the population? Or could the pattern that we see in the scatter plot plausibly happen by chance? And another question that we might try to answer is, in the population, how much will the predicted value of y change for each increase of 1 unit in x? That's the slope. So we're going to be making some inferences about the slope. We're going to be estimating the rate of change for population and also testing claims. All right, the regression model. You guys are familiar with our y hat is equal to a plus bx. So just remember, in all of these notes, b is referring to our slope. So don't get the a and the b confused. So the slope b and intercept a of a least squares regression line, those are considered statistics because we calculate the regression equation from data from a sample. And so if we were to take a different sample, obviously we'd get a different regression equation. And so if we want to do formal inference, then we need to know a little bit more about the unknown parameters that A and B are estimating. And the parameters appear in what we often call a model of the process that produces our data. All right, some assumptions. And these are just kind of like what we have to kind of go in assuming is true. So if we have n observations on an explanatory variable x and a response variable y, so we're looking at n now represents the number of ordered pairs instead of, so n equals the number of ordered pairs, because we're going to have an explanatory and a response. So n is corresponding to the number of ordered pairs. And our goal is basically to study or predict the behavior of y for any given value of x. And so there are a couple of assumptions that we're going to assume going in, and that is that the response is going to vary according to a normal distribution, and that repeated responses are independent of each other. We're also going to assume that the mean response, so for any x, I'm going to get a different response, but the mean response for y is going to be in a straight line relationship. So notice that this equation here looks a little bit different than the equation on the previous page. And that's because the equation that we have here is for the population. So remember how we use Greek symbols to represent population parameters and then regular letters to represent our sample? Notice that we're using alpha and beta here to represent the y-intercept and slope of the population. They are not the same as the alpha and beta that we were referring to with the type 1 error and the power. Okay, so they're different. We're just using those as our variables for slope and y-intercept. So in general, I'm going to do a little table here. So we have our slope, we have our y-intercept, we have our sample, and we have our population. The slope in our sample we're going to call b, lowercase b, just a regular plain old b. And our y-intercept from our sample we're just going to call plain old a. But in the population, we're going to refer to the slope as beta and the y-intercept of alpha. And so those are the things that we're trying to estimate. Our equations are going to look a little bit different too. The actual linear regression equations that we come up with are always going to be of the form where y hat is equal to a plus bx. Let me fix that. But in terms of our population, we're looking at the mean response of y. So I'm looking at mu of y is going to equal whatever the population y-intercept is plus whatever the population slope times x. Okay, so this is the equation that we're going to be working with. This is the equation that we're trying to estimate. Okay, and that's just notation. So beta and alpha are unknown parameters because they're describing the population. And the standard deviation, so here we're describing the mean of y, the mean response. The standard deviation is going to be unknown, but we're going to assume that it would be the same for each value of x. All right. All right, so conditions for the regression inference. This is more along the lines of what we were saying before. The mean value of the response is going to follow our true, this is our true population regression line, which we're never going to know unless we do a census. And that all the values of the response variable follow a normal distribution. So this is basically what it would look like. Every time I take a sample, right? So if I have a sample, think about the GPA problem that we had with all the kids that were watching TV. So I take a sample of 10 students and I think, okay, well, if you're watching on average 10 hours, I'm going to have a couple students that say, yeah, I watch TV for 10 hours. I'm going to get their GPAs and I'm going to take an average. That average, if I take a different sample, is going to vary. So it'll be the same number of hours, but the mean GPA is going to vary. That variance is going to be a normal distribution. If I have a group of students and I'm looking at kids that maybe watch 12 hours of TV, I'm going to have a bunch of different GPAs that correspond with 12 hours. So each of my Y's, each of my responses now are going to follow a normal distribution. And that's what this graphic is basically representing. Okay. When we're looking at inference, when we're taking our linear regression equation, the slope we get is considered an unbiased estimator of the true slope. The same is true for our y-intercept. It's an unbiased estimator, and that is ensuring that we have a simple random sample of data. If there's any kind of bias in my data gathering techniques, then that's not going to be true. So you do want to make sure you're dealing with a simple random sample. The standard error about the line, and this is something that I don't think you actually have to use this formula. I believe it is on your formula sheet for the AP exam. But when you're doing the tests on the calculator, it'll calculate the standard error for you. A lot of times you're going to be given the output from like a Minitab program, and so it'll actually tell you what the standard error is. So I don't think you actually have to know that formula. But because we're dealing with mean and standard deviation again, we're dealing with a normal or a t-distribution. And since we don't know the standard deviation of the population, we're always going to be using a t-distribution. But notice this time the way our degrees of freedom are defined. It's n minus 2, and that's because we're dealing with two variables. So we're dealing with a t-distribution, but our degrees of freedom are now defined as n minus 2. Okay. All right. So when we're doing inference for regression, there are 5 total conditions. And so it's important that we think about each of them in the process. For example, the straight enough condition. This is pretty obvious. If I'm going to be doing regression about a linear equation, I want to make sure my data is linear. If I do a scatter plot and I see a curve, is it going to make sense to do a straight line regression? No. So if it's curved and I'm doing linear regression, I'm going to stop. There's no sense in going any further. So that's the first condition. The data obviously has to look approximately linear. It doesn't necessarily have to be a strong association, but it has to be an association that isn't clearly nonlinear. So if there's a definite curve, you're done. Independence and randomization, again, because we're dealing with different data points, you want to make sure, and so this condition is the same as it's been. Independence and randomization. Also, when sampling without replacement, you want to make sure your population is at least 10 times the sample size. So these 3 conditions are the conditions that we've been seeing the whole time. The other 2, so this straight enough condition you're going to show in your scatter plot. The third one, or the fourth one, has to do with equal variance. And this is making sure that the y values are spread evenly over your regression equation, and this is what you're going to show in a residual plot. So that's the second graph. And then this is the one that's new. It's the normality assumption, but we're looking at the residuals. So all of the residuals, which we saved in list 4, you're going to do a normal probability plot on your residuals. So each one of your inferences, you have the same 3 conditions that we've always had, the independence, randomization, and your population has to be at least 10n. The 3 that are new are your plots. You're going to have a scatter plot. You're going to be able to look at your scatter plot and say, yeah, the data looks pretty normal. Or it looks straight enough. You're going to do a residual plot and show that the points are evenly scattered about the line. That's our equal variance. And then you're going to do a normal probability plot on your residuals and show that it's normal. And then those are the other 3. Okay, confidence intervals. We're going to start here. All of our confidence intervals follow the same pattern where we take our estimate plus or minus our critical value, and our critical value is determined by our confidence level, and then we multiply by the standard deviation or the standard error. All confidence intervals have that same pattern. So the B here is referring to the slope. So you're going to take the slope of your regression equation. You're going to determine your critical value t, depending on what your degrees of freedom are and the confidence level. And then the standard error of your slope is this formula, which again, you're not going to have to actually plug anything in, I don't think. If you have data, your calculator will figure that out for you. And the other alternative would be that you're given a computer output that has the value on it. Again, since we're dealing with a t-distribution, we have degrees of freedom, and the way they are calculated is n minus 2 because we have 2 variables. All right, so let's take a look at an example. So this is one where you're given some computer output. We've seen this output before, but we didn't know what half of those numbers represented. So it says many people believe that students learn better if they sit closer to the front of the classroom. Does sitting closer cause higher achievement, or do better students simply choose to sit in the front? So to investigate, a statistics teacher assigned 30 students to seat locations in his classroom for a particular chapter and recorded the test score for each student at the end of the chapter. The explanatory variable in this experiment would be the row to which the student was assigned, where row 1 is in the front. So it says that this is an experiment. What are the words I'm looking for? What are the foundations for a good experiment? What needs to be true? Random assignment. Does it say anything about randomly in here? No. So without random assignment, can we make inferences about causation? No. So what is the first assumption we're going to have to make? We're going to have to assume that they were randomly assigned, even though it doesn't say it in the problem. What else is important in an experiment? Control. Do we have any control here? Not really, right? There's nothing to control against. And then what else? Replication. Do we have replication? Yeah, we have 30 students, so that's okay. And the last one, no, population, has to do with we have to have comparison. So we have to have something to compare to. And so is there any comparison here? It is a way of controlling. Yeah, they kind of go together. But it's not like I set them, I have their current test scores and then I move them to see if it changes, or if, I'm not comparing their scores to anything. I'd probably want to change their seats and see if there's a difference between the seating arrangements. So this is not a very well-designed experiment, but nonetheless, we're going to continue. So let's take a look at the information that you're provided. We have only looked at, not even the S. The only numbers that we've looked at are the numbers in that first column and then the R squared. Those are the only things that we've looked at. Marshall, you still with me? Okay. And so both of these numbers that we have listed under coefficient provide us with the sample, slope, and y-intercept. The question is which is which. Does anybody remember which is which? Say that again? The slope is the bottom one. The one that is next to constant, if you think about it, your y-intercept is the constant. The row, that's our x variable. So the number that's next to that would be the coefficient of x. So this is our slope. And so if I wanted to write the regression equation, I'm going to say that y hat, don't forget to put a hat on it, is going to be equal to 85.706 minus 1.1171 times x. But now, if you take a look at those other columns, I know we ignored them at the beginning of the year, but do those terms now look familiar? What does SE of the coefficient stand for? Standard error, T. It's our T value. Now, and this P, what do you think this is? This is the P value, the probability of our sample. And so the T and the P go together. This is not the T that we're going to use in our confidence interval. It's the T that would correspond to our slope and y-intercept if we were doing a hypothesis test, which we'll do. Okay? So let's take a look at some of the questions. So it says to write the equation of the least squares regression line and interpret the slope. So we said it was 85.706 minus, actually I have this written down somewhere. Okay, so how would you interpret the slope of this line? It is. Use it in context. That's not what the slope represents. For every row you move back. Your score. Now be careful about the next part, because remember, it's just estimated or it's an approximate. Your score is estimated. And we'll assume that's in points, maybe. Okay, so remember, when you're interpreting the slope, it says x increases by 1, the y value is either increasing or decreasing by the value of the slope. And then you want to make sure that you actually are using the correct variables in the problem, and making sure you're using the context. So in part B, it says to identify the standard error of the slope. So which of those standard errors represents that of the slope? The second one, so 0.9472. Okay, and the standard error, it's similar to the standard deviation. It's basically describing, or we can basically expect the rate of change, because that's what slope is. We can expect the rate of change to vary about 0.9472 points per row in repeated sampling. Do I need to write that out? Does anybody need me to write that out? So we can expect the rate of change in the decrease in score by row to vary 0.9472 points in repeated sampling. Okay. Now in letter C, it says to assume the conditions for inference are met. Remember, there's 5 of them when we're doing linear regression. It says to calculate the 95% confidence interval for the true slope B. So in our formula, it says we're going to do B plus or minus T star times the standard the standard error of B. Well, what was the slope? Plus or minus. Now remember, the T that's listed in the table or listed in the output is not the T that we would use for the confidence interval. So how would we figure out the critical T value for our confidence interval? What information do we need to know? The degrees of freedom and the confidence level, right. So we know the confidence level is 95%. Now if I was using a normal distribution, I would just use 1.96 for my Z value, but I can't do that with T. So if I'm dealing with a middle 95%, I'm going to end up having to use the inverse T distribution, and I have to think about the area to the left. And so what area would that be? 0.025. Okay, and then we also need to know the degrees of freedom. And how many students were there? 30, and so we're going to do 30 minus 2, which gives us 28 as our degrees of freedom. So now we can go into the inverse T distribution. And so that's option 4. I've got it in there already. And so the value we get for T is going to be negative 2.048. But remember, when you're putting it into the formula, you want to make sure you take the absolute value of that. And then what about the standard error? That's given to us, right? So 0.9472. So when we're calculating the interval, we want to do the subtraction first. So we'll do the negative 1. And that'll give us our lower bound, so it's a negative 3.06. And then if I just hit second enter and change the subtraction to a positive, to a plus, that'll give me the upper bound. All right. And so that gives me a positive 0.823. So tell me what you mean by not significant. Because we're not doing a significance test, we're looking at a confidence interval. What are you saying? It's 0.823. Yeah, sorry, that's just a decimal value. So notice that our interval goes from negative 3 to positive 0.8. What does it include? It includes 0. So remember, if we're talking about a slope and a rate of change, what does it mean if the slope is 0? Then there's no change. So since 0 is contained in this interval, can I really conclude that there's a change in your score based on where you sit? No. Now, if 0 was not included in that interval, so for example, let's say both of the numbers were negative, then I would say that that we are 95% confident that the decrease in score per row would be between 3 points and negative 0.8 points. I mean, all I can say here is that we're 95% confident that the change in score is from a loss of 3 points to a gain of 0.8 points. That's what the literal translation of that unit of that interval would be. So let's write that down so you know how to write it. And I'm just going to kind of round a decrease of 3 points to an increase of 0.8 points. So it really doesn't help us conclude whether or not there's a, to answer the question, like does proximity, does being further away from the front hurt your score? Well, all I know is that I'm 95% confident that the answer lies within that interval. So it doesn't really answer the question because 0 is included in it. So part E, we can take it one step further. Based on our interval, is there convincing evidence that seat location affects the scores? And here we would say since 0 is contained in the interval, we cannot conclude that there's a change in scores based on seating location. Or based on proximity. Okay. While we're working on this problem, what I'd like to do is just go ahead and jump into the hypothesis tests, and then we'll come back and look at what happens, how we handle it when we have the actual data. Because when you have the actual data, you have to go through the whole process. So let's jump to hypothesis tests and skip the next example for a second. Okay, so if you think about when we're doing tests of significance, our null hypothesis usually represents that there's no change or no difference or no association. Marshall, I need you to be with me, please. And so when we're dealing with a slope, when we're dealing with regression, if I'm talking about no change or no difference, then that means I'm dealing with a slope of 0. So our null hypothesis is going to be that the true slope, and notice that we're using the letter beta because that is the population slope. So we're saying that it equals 0, which is essentially saying that there's no true linear relationship between x and y. So that is our null hypothesis. And then the test statistic is just going to be the standardized version of our least squares slope. Okay. So if I want to test the null hypothesis, I'm going to standardize my t-value, which is taking my sample slope minus the population slope. But if you think about it, we just assumed it was 0 over the standard error. So this is the same formula that we've been using the whole time when we take our actual value minus the mean and divide by the standard deviation. And then we still can have an upper tail test where we assume if beta is positive, then we're assuming a positive association between the variables. This represents a negative association between the variables. And maybe we sense that there's an association, but we don't know if it's going to be positive or negative, and so in that case we would do a two-tailed alternative. Okay, but this notation, this is all stuff you're familiar with. Just now our parameter is beta. We're still using the t-distribution. Okay, so referring back to the example that we had before, what would you expect the relationship to be? The farther away you are from the front, the higher, the lower? What would you expect your scores, your performance? The lower, right? The further away from the front, the expectation was that the scores would drop. So our null hypothesis is going to be that beta is equal to 0, that there is no difference in scores. The alternative, though, is to say that there would be a decrease in performance the further away you are. And oftentimes you're asked to also support your hypotheses in words. And so you might just say, a decrease in performance. It doesn't really fit, sorry. Okay. The nice thing about having the output is that everything you need is right there in front of you. There's really nothing else. You just have to be able to pick out the right numbers. So when I'm writing my probability statement, remember we start with the statistic. And the statistic in this case is the slope that I got from my sample. And what was that number? Negative 1.1171. We're doing a lower tail test, so I'm going to put a less than symbol there. Marshall, stay with me. Okay? Then what do I need to do when I'm doing a test of significance? What's the next step with my probability statement? Standardize it. And do we know the value of t? We do. This is the t, well, sorry. The t value is going to be less than negative 1.18? And then we're told the p-value is 0.24. Okay, so all the information you need is right there. You do want to report the degrees of freedom. And so we'd say the degrees of freedom is 28. And you also want to be able to, in this case, the output is given to you. But if we were physically using the data to do the hypothesis test, you'd want to make sure that you're stating the distribution that you used. So we'd be using a t-distribution for the slope. Or for regression, if you wanted to say that. Now, is this result significant? Can we reject the null hypothesis? Is that a yes or no? And so what does that mean in terms of the problem? We cannot conclude what? Okay, that works for me. We cannot conclude that seat location affects test score. In fact, we probably want to be a little bit more specific because we were looking at a decrease. So we cannot conclude that seat location, let's say, decreases test scores. And that way we're referring back to our alternative hypothesis. Okay, I want to give you guys a short little break. Okay, so we are going back to example number 2, and we're going to go through the process of determining the least squares regression line, finding the slope, interpreting it. We're going to construct a confidence interval for the slope, and we're going to do a test of significance for the slope. So when you're given the data, though, it takes a lot more work because you actually have to check all of the conditions. And like I said, there's 5 conditions now. So now that your data is entered, let's go ahead and determine the equation for the least squares regression line. So if we go to stat, calc, it's just data from another problem. Whoops. You did. My train of thought is now ruined. Okay, so linear regression, you can use either equation you want. Just remember that, the calculator will call A and B different than what our test of significance does. It asks for a frequency list, but we didn't enter in any frequency, so we're not going to worry about that. We want to store the regression equation in Y1. All right, so just pay attention to how the equation is written. So in this case, my A is my slope. So we're looking at 0.03x plus 4.53. Let's just round to 3 decimal places, or two decimal places. So, all right. Did everybody get that equation? Okay, so what does the slope represent? We're talking about people. I guess I should probably read the question. So do customers who stay longer at a buffet give larger tips? So Charlotte, a statistics student who worked at an Asian buffet, decided to investigate the question for her second semester project, which I am not making you do. You can thank me later. While she was doing her job as a hostess, she obtained a random sample of receipts, good for her, which included the length of time in minutes and that the party was in the restaurant and the amount of tip in dollars. Here are the data. Let's assume that she has scaled it so that this is per person and not for like a table of 8 people that she's only making $7. So what does the slope mean? For every minute. The estimated tip increases, we could say by an average of what? Oh, yes, 3 cents. Okay, so for every minute, we should probably say at the buffet, because that's not necessarily going to be true at every restaurant. The estimated tip is going to increase by an average of 3 cents. Okay? All right, let's take a look at the next question. This is where you have to check all your conditions for inference. Okay, a lot of this you've done before. The only thing that's new is doing a normal probability plot of your residuals. Everything else you've done. So let's start with the scatter plot. We obviously, even before we do linear regression, we should first see if our data is linear. So let's go ahead and turn on a linear or a scatter plot. I do want to make sure though that I'm pulling my data from the proper list, so I want to make sure I change that back to list 2. And then we can zoom 9 it. Hi, Mr. Smith. So is that linear enough? All right. Okay, so is this linear enough? Sorry. It's linear enough. I mean, it's definitely not a very strong association. So we can say, whoops. So although it's not a strong association, it is relatively linear. Okay, so you do want to make sure, guys, that when you are giving a plot, that you're sketching it and that you're making a comment about it. So just drawing a picture of the scatter plot and moving on to the next condition is not going to be enough. You have to say something about it. So we can say, although it's not a strong association, it is relatively linear. So that meets that condition. What about the independence and the random? It said in the problem that she was looking at random receipts, so that was given. What about the independence? We're going to have to assume it. We're going to have to assume that customers weren't like, I'll wait 5 more minutes if you do, and I'm not going to leave more of a tip. So we're going to have to assume independence here. The 10% condition is basically the assumption that the population is at least, what? Could you turn that off, please? It was right there. Assume or given, yeah. So what do we have to assume? The 10% condition. The population has to be at least what, guys? 10n. And what's n in this case? How many receipts did she look at? Will you count them for me? Because we need to know what they are. 12. Okay. So can we assume that there are 120 customers at this restaurant? That's why we're making it an assumption. Okay? Now, the next one has to do with the equal variance of y. This is where you have to sketch your residual plot. So yes, you do have to go back into your lists. Okay? It is a lot of work, I know. We're going to pull up our y variable and evaluate it over list 1. And then subtract list 2 minus list 3. Okay, everybody should be doing this with me. Shane, put your phone away. Okay, and then we want to do our residual plot. So if we go back into our plot menu, I'm going to stick with the scatter plot. List 2 minus list 3 is going to go into list 4, because it's your actual minus the predicted. And so when I do my new scatter plot, I want to make sure that I call my y list list 4. And so that is my residual plot again. Now on the test, when you're constructing these plots, you want to make sure you label this is the scatter plot, this is the residual plot, because if you don't name them and you just have a bunch of dots all over your paper, the graders aren't going to know which is which. And so what does the residual plot tell you? Do we have equal variance of y? Yes. So we have equal variance in our y values. That condition is met. And so the only new thing that you're asked to do is a normal probability plot for your residuals. Now you've been expected to do normal probability plots with small data sets the whole time. Not a lot of you are doing that, but that is the expectation. So to do a normal probability plot, we're going to go back into our plot menu. The normal probability plot is that last graph. It almost looks like a line plot. And then where are our residuals? Where did we store them? Just in list 4. That's where all those are the differences between the actual and the what we would predict. Once you do that, you're going to go ahead and zoom 9 it again. And what are we looking for in a normal probability plot? It's that relatively linear. So you want to say the normal, make sure you label it, probability plot is linear. So you can say it's approximately normal. So real quick, this is a little bit off the subject. Students that came in last Saturday, we did some FRQ review, and we actually looked at the way the FRQs were graded. And it turns out, so you know how like when we're looking at, unless if the population says that the distribution is normal, that's great. But a lot of times we're having to use the central limit theorem saying, you know, that since n is greater than 30, the distribution is normal. If you don't write the word approximately, you cannot get full credit. So just as a general rule of thumb, unless it says in the problem that the data is normal, when you're checking that condition, the n is greater than 30, make sure you use the word approximately normal, because you won't be able to get a 4 if you don't. Okay? That's kind of a silly thing. That's why you're doing the residual plot, or that's why you're doing the normal probability plot. When your data set is too small, that's when you have to do the normal probability plot. And if you don't have the data, that's when you have to assume normality to continue. All right. So we're going to use the linear regression t-interval command on our calculator. Now, I will say the older calculators do not have this command. So if we want to do an interval for our slope, if you go to your stat and test menu, some of the older calculators, they're actually at the very bottom. They're the last, or 2 of the last commands. You'll see a linear regression t-test and a linear regression t-interval. If you do not have the t-interval, then you definitely want to make sure that you borrow one of my calculators for the AP exam, okay? So we're going to do a t-interval. And just like with all of the other tests that we've done and all the other intervals we've done, the calculator pretty much prompts you for everything. It wants to know where the data is stored. Remember that we're going back to our original x and y, so we're going to go to list 1 and list 2. You're going to put in your confidence level, which is 95%, and you want to tell it where the regression equation is stored. And then you're going to let the calculator do the work for you. I know. All right, so the confidence interval is given. Just remember, you want to make sure that you label, so the linear regression t-interval. Remember, you want to make sure that you label your inference method. And then when you're reporting a confidence interval, you need to make sure that you report the confidence level as well. And so you're asked to interpret the interval with respect to the problem. Okay? And in this case, if the question is asking us, if we go back to the original question, she wants to know, let's see, where did it say? Do customers who stay longer at the buffets give larger tips? Ultimately, that is the question that she's trying to answer. So if we look at this confidence interval, what can you conclude about the answer to her question. We're not asking about significant. Think about the question that's being asked. Do customers who stay longer leave bigger tips? What number is in that interval? 0. So, are we going to be able to conclude that they leave larger tips? No. So all you have to say is, since 0 is contained, and I would include the 95% confidence. Or you can say, since 0 is contained in the interval, we can be 95% confident that there's no difference in, or I guess that tips do not increase I want to say this differently. I'm sorry. We can't say, I'm sorry, I'm going to change this. Because remember, we don't want to accept it. So what we'll say here is we can't say that customers who stay longer leave larger tips. You could also say that the rate of change in tip per minute is anywhere from a -2 cents to a +8 cents. I mean, that you could say it that way as well. You'd want to say we're 95% confident that the changes between those two values. But I think it makes, to answer the question is what's really important here. And so we really can't conclude that they leave larger tips. So let me show you now, if we skip back to the significance test, how would you state your null and alternative hypothesis? Remember, the null hypothesis is always that the slope is 0. What would we expect to be true here, before looking at the data and everything? That it would be more than, right? Yes. And so now if you look at your, if you go back to the test menu, your calculator will perform the test for you. So if you go to stat test, I would just go back up the other way. You want to do a linear regression t-test and make sure that you're calling everything up. Your alternative hypothesis is that 4th line. And again, your calculator will give you all the information you need. You just need to make sure that you say that you're doing a linear regression t-test. Remember, your probability, again, has to include the 3 parts. The true, or what we observe to be our slope, so you'll have to scroll down a little bit to see it, of 0.0301, so it's going to be greater than 0.0301, translated into a t-value, the probability that t is greater than 1.231, and then our p-value is 0.123. Always report your degrees of freedom, and then state your conclusion. Okay, and so is the result significant? No. Can we reject the null hypothesis? No. So can we conclude then that tips increase with the length of stay? No, we can't make that conclusion. Okay.